Let us now take a look at acid-base titrations. Now this topic has lots of technical words used to describe the various bits of apparatus, or the names of the various different chemicals are, but also there are calculations too. It's one of the most crucial topics in all of A-level chemistry, so let us begin. So where did this method come from? Well, we have to go all the way back to 1791. François-Antoine Henri Dacrozil was the Frenchman that invented the burette, the graduated narrow cylinder with a little tap at the bottom with which you could add one liquid to another. And then fast forward over 100 years into the 19th century with Joseph-Louis Gay-Lussac, famous, of course, for inventing the third gas law. It was he that put together all of the elements that we would now recognize today as a titration. So what is this thing, titration? Well, it involves a burette held vertically above a conical flask. Now, here are some of the little details. You're going to put one substance in the top, and you're going to add it to another substance that is in the flask. To do that, you're going to control the stopcock, which is the little tiny tap at the bottom of the burette. When the handle of the stopcock is vertical, and so it's forming a line like parallel to the burette itself, then it's going to allow the liquid to flow through it, turning it at right angles to it, like forming a little wall against the liquid, will stop it from flowing. Here's another piece of interesting information. The actual conical flask itself, sometimes known as an Erlenmeyer flask, it is conical for a reason. It's flat bottom so it doesn't roll off, but it's also the sides of it are smooth and clear and can be looked at from the angle at which you would stand whilst operating a titration. You're looking at it normal to the surface so that you can spot any colour changes or any differences that's occurred in your chemical more easily. Now, an important thing when doing chemistry is calling glassware by its right name. That way, when you're describing the experimental procedure, you're going to get all of the marks for using the right scientific vocabulary. Now, as well as the burette, it's also important to refer to the glass container underneath as the conical flask. There's one more piece of glassware, which is really important. On this diagram here, you can see the conical flask is number 4. Next to it, number 5, is a volumetric flask. Now, this is going to be used to prepare the solution that goes into the burette. It is a flask that's designed for making very accurate concentrations of liquids up. So let's have a look at that in more detail. So here, the volumetric flask, put into good use by Joseph and Geneviève Gay-Lussac in their experiments in the 19th century. Flat bottom to stop it rolling off the table, narrow neck, which meant that very accurate volumes could be put into it. It's quite insensitive to more or less volume when you're filling up the bulbous section, but when it goes into a narrow neck, every little drop will actually cause quite a substantial change in the height of the liquid. So measuring the height of the liquid within the flask, you'd obviously measure it to the bottom of the meniscus, lining it up with that little line that you can see, which tells you when you've hit 100 millilitres. Now that meniscus, why does the liquid take on a curved surface like that? Well, it's to do with the balance of two things. Adhesion between the water molecules and the sides of the container versus cohesion between the water molecules and themselves. If the forces are stronger of adhesion, then it will start to climb the sides like water. But if the cohesion is stronger, it'll try to avoid the sides, humping up in the middle like mercury. Irrespective of what it's doing, the flat section in the middle of the meniscus is the place that you would want to line up with a little graduated mark. Now, depending upon the size of your flask, there's different tolerances in terms of what is the smallest amount you could measure. In a 100 centimetre cube flask, it's going to be plus or minus 0.2 centimetres cubed. And in the larger 250 centimetres cube flask, it's going to be plus or minus 0.3 centimetres cubed. Now, these are details you're going to have to remember later when you are asked to make suggestions about what the accuracy of a certain experiment is likely to be. So let's talk about making up that standard solution in the first place, that which we're going to put into our burette. Now, generally, we're going to make this from a soluble powder mixed with a liquid, but it has to be a very accurate concentration. So how do we achieve that level of accuracy? Well, there's a process for making up a standard solution, and this is it. First, we need to measure out the mass of the solid using a top-hand balance and the substance in question. We'll add it to a small beaker, and then we'll add a little bit of distilled water, less than the total volume that's required. And then what we're going to do is we're going to stir it and stab it and crush it and mix it until it is basically all dissolved. If there are large crystals in there, you're going to have to go at it for quite some time. But then eventually, when it has all dissolved, you need to just then rinse off any substance that's stuck to the spatula. So give the spatula a clean with the distilled water, with all of the drops going back into the solution, so that you have caught every last drop of that substance. Next, you need to add that liquid into the volumetric flask. Use distilled water to swill the beaker afterwards to again ensure that every last tiny bit of your substance has ended up at the bottom of the volumetric flask. Once it's all in there, you can then make up the solution to the required volume, adding more distilled water until the bottom of the meniscus lines up with the graduated fiducial mark on the side of your volumetric flask. And now for the most exciting part of all. You place a stopper in the top of your volumetric flask, and keeping one finger, or two, on the stopper, and the fingers on the other hand on the bottom of the flask, you're going to invert it. You're going to tip it upside down to allow the bubble to move the entire length of the flask. And then you write it the right way. You're going to turn it upside down about 3 times, being careful not to take your finger off the stopper, otherwise your solution will be all over the floor. This is now the correct concentration. Now the amount of this titrant, which is what it now is going to be called, that's going to react with the analyte, the substance in the conical flask, it's going to be known as the titer. And so we're going to use these words to describe it from now on. So why a burette? Well, it's just really easy and convenient, and for the sort of chemistry we need to do at school, accurate enough. It's accurate to plus or minus 0.1 centimeters cubed. But greater precision is possible with other devices. Rather than using a burette, you could use a 25 centimeter cubed pipette, which would have an accuracy of plus or minus 0.06, or even a 10 centimeter cubed pipette, which has an accuracy of 0.04 centimeters cubed. Now, the tolerance of an experiment is defined as the smallest division in the apparatus. And so, therefore, the smallest division on the burette is 0.1 centimeters cubed. Now, that means that it can actually measure to the nearest 0.05 centimeters cubed, because we can measure basically 0.05 above or 0.05 below any particular marker that we found. So that means with burette readings, we always need to record them to 2 decimal places. This is going to be important later, 24.25 centimeters cubed. And if you think it's landed bang on the money, then you must refer to it as like 24.00 centimeters cubed, maintaining the precision in all of your results. Now, doing a titration is not just about tricking all your substances together and mixing them. Oh no, there are slight techniques in which you're going to have to employ to make sure that you get good results. And one of them is getting rid of the air bubble that might sit immediately below the stopcock. So what you can see is here on the left, there's an air bubble underneath. I've not flushed the burette. I need to let that air bubble get pushed out by some of the liquid. Otherwise, the first few drops in the volume that I detect at the top are actually not going to have added to the analyte. It's just going to be basically pushing the air out. So we need to push the air out first, stop the stop clock, and then replace the flask underneath with our analyte so that we're ready to go. And so here it is. We use a special burette clamp to hold our burette in place. We make sure that the stop clock is turned horizontally, and then we add the titrant to the top, making sure that the amount of volume falls somewhere between the smallest and highest reading on the burette. It's a mistake to believe the burette must start at its 0 point. It has to just be somewhere between these two. Now what we're going to do is we're going to first of all turn the stopcock to get rid of the air bubble at the bottom of the burette, and then turn it back again, then switch and place underneath analyte with a few drops of indicator. Ultimately, we're going to be looking at the point where this neutralizes, and so the indicator is going to tell us when that happens. Now we need to do this multiple times until we get results that are concordant, which basically means the same as each other, the same within 0.1 centimeters cubed, the accuracy of the burette itself. If you were going to do this with the pipette, then the concordance would need to be to the accuracy of those devices. Now this is how you should always record your results for a titration. So if you have a look at the individual rows there, well, first of all, what are the columns? The columns are individual trials. You're going to do it multiple times. You're going to have, for any particular thing, you've got to record all of the raw data and then show how that data has been processed. So the final burette reading and the initial burette reading of every single trial needs to be recorded. And then the titer, which is the difference, is just how much of the titrant got added. And then once you've done it for all of your trials, you can take a mean. Now the number of decimal places should be the same across rows and down columns. It should always be to 2 decimal places. But to gain concordance, what you can do is you can reject non-concordant results, do them again, or alternatively take an average of your best 2. You're trying to find results that are concordant with each other. There are many different calculations you can do in titration, and if you're interested in the full range, then go and have a look for my other videos where we go through them one by one. But principally, probably the most basic is where we have a titrant, an acid being added of known concentration and known volume, to an alkali down below whose concentration is unknown but its volume is known. We can work out the concentration quite easily. All we need to do is work out what the number of moles of the titrant was. So if we know the concentration and multiply it by the volume, we get the number of moles for the acid from the formula. Number of moles is equal to concentration times volume. Now once we have that, we need to know what the moles ratio was between the acid and the alkali that was reacting. So we need to write out the balanced equation, and we need to do that every single time. And if it's a 1-to-1 ratio, we know that 1 mole of acid has neutralized with 1 mole of alkali, and so we will now know how many moles of alkali must be present in the analyte. So having the number of moles and dividing that by the analyte volume would then give you the concentration in moles per decimeters cubed of your analyte. A second but very common type of question is to identify a carbonate or a hydroxide, or basically using information deduced from your titration to work out the identity of an unknown chemical. So here, for example, we've got a titrant that is known to be hydrochloric acid of known volume and known concentration. And with the analyte, though we know the amount of mass we've added, we don't know anything more about the analyte other than how much volume it has and that it is a carbonate of some sort. So for this whole thing, we're trying to work back to find the molar mass of this chemical, and from that we're going to then be able to work out what it is. So the strategy that we have to employ here is, first of all, as with before, calculate the number of moles of the titrant from the formula N equals CV, and then using a balanced equation, work out the number of moles present in the analyte. Now in this case, it's going to be a 1-to-2 ratio. Then, once you've worked out how many moles of analyte, you can then work out the molar mass from the N equals M over molar mass, so sample mass divided by molar mass. And so then we can work out what the actual mass, molar mass, was of this substance X2CO3. And so once we've done that, we can subtract away the molar mass of the CO3 and then divide by 2, and it's going to tell us the identity of the unknown chemical. Now, that's easy to say, but it's much more difficult to do. So if you want to watch a complete workthrough of finding the identity of an unknown chemical via titration, then I suggest that you like and subscribe and go hunt down that video.